Okay, good morning. So today the reminder of the Simpson method, and after that, a reminder of this avoidable method, and the first one, the composite and the recursive, and then try to get a motivation for the Romberg method of motivation from these reminders, and then talk about it and take an example. After the Riemannian way of integration or approximation, and after the other one, we thought of another way of integration or method that we hope it will be better in terms of error being small, or the order of the error being large. So we divide A to B to n segments, and each segment we take m plus 1 points of it. So here we have x0, xm, x2m, up to x2mn. For the difference between xm and x0 is mh. We have m steps here. So we have here m plus 1 parts. Okay? And now we will talk about only the first segment. And after that, we sum all these segments. Okay? So in the Riemannian way, what was m? If we want to approximate the integral by only saying that the integral is the sum of the function divided by
1. 1.
Yeah. 0. M equals 0. So we took only this value, and we took the sum of it divided by. Okay. So f multiplied by h, that's the rectangle. And if m equals 1, it is the trapezoidal. So if m equals 1, we use 2 points, which are these, 1 and 2. There is no in-between points. And if n equals 2, this is the same. That we call it the Simpson curve rule. Okay, so how we use the Simpson? If m equals 1, so that's the Simpson curve rule. And yes, and I call it the third rule because of this word. And there is, if you use 4 points, not 3, and they call it the okay. So it's only because of this stuff. So what we do if we use the Simpson rule? So what's our way when we use m plus 1 points? What do? We interpolate the function there using these points. Okay, and then make the integral, calculate the integral. Okay, so we approximate the function by a polynomial of order 2, quadratic polynomial, and then make the integral. Okay, so that's our way. So the function is this, and here between x0 and x2, we have this quadratic approximation or interpolation of the function. This we have a quadratic interpolation of the function. Okay. And the integral is the area under this quadratic function. And when we make the interpolation, and calculate the integral only in the first segment, we get that the answer is h3 f of x0 plus 2f of x0 plus 4 plus f of x0 plus 2. Okay.
What is H?
H is this. Now H is x0, x1, x2. And we say that the error is of h to the fifth, and we'll talk about this in a minute. And when we use the composite trapezoidal method, which is taking all these segments from A to B, we have the integral here plus the integral here plus the integral here. So we have the evaluation or the approximation of the sum of our approximations here, like this. And the error is the error here plus the error here plus the error here. And each error can be written as minus h to the fifth over 90 multiplied by the evaluation of the fourth derivative of the function at some psi j, where psi j is some point between what and what? Between x2j minus 2 and x2j. So we have here psi 1 and here psi 2 and here psi 3. Okay. And if we add all these errors, we have this sum, the psi j's, and 1h from these is b minus a divided by the number of the points, okay, which is n. And this will be an average taking the n in the denominator. Okay, so we will get that the error, the total error, is of order of h to the fourth. Okay. Good. Okay, we have to write this down. So the total error is of order h to the fourth when we talk about the composite way. Any question?
Do you mean there's a mistake in the document?
No, there is no mistake in the document. There is another step that we have to do. Only to type that this is h to the fourth and multiplied by some evaluation of the function at some point. Okay, because the sum of, for example, from a j1 to n, it is to n. It depends what you call n, no problem. What is this?
Yeah.
Yes, and I can write it as what? If this is a continuous function. There is some psi that this equals to. Okay.
Oh yeah, fine.
It's the intermediate.
That's the goal. Yeah.
Parameter. Okay. So
How related to
the h2.
No, you keep saying h to the fourth, but it says h to the fifth.
So that's h to the fifth divided by 90. The sum of f prime prime. It's the sum, and this sum has n terms or n over 2 terms. This n depends on h. It's 1 over h. So like 1 over h. So what is this? This is h to the fourth over 90 multiplied by b minus a over n, that's h, the sum of f. And this is f prime prime at some point. So the error goes like h to the 4. It's always like this.
Why is it over 90?
So it's because of the term, because of the half, it is over, I think, 180. Doesn't matter. Okay. So, EA5. Some, no, I didn't try it. Oh. So this 1/90, we'll talk about it in a minute. But any questions up to now?
Why the sum is up to n and half 2?
Because
Divided
n, this is n, okay? No. So what's called there n, it is n m in this notation, okay? Yes.
So did you evaluate the input value?
Hmm?
How did you evaluate the input value?
How did I? So again, I made the interpolation. I didn't tell you. Until now, I didn't tell you. But I made the interpolation here. I know how to make this interpolation, Lagrange interpolation. This is a polynomial of order 2. And then perform the integral calculus. That's the answer. Okay, so you know how to build this polynomial. We will make a general case. Questions? Okay, so again, it goes like h to the 4th. And here's an example. If we want to calculate this integral, we can take h to be 1. You see why h is 1? Because here are only 3 points. And I only take the rule for the whole segment, a to b. And this is h, so h is 1. And I make the same, or I calculate the same integral using another h. What is h here? I take n to be 4, and at each segment I have 1/4. So the segment is 1/2, and h is 1/4. Okay, so the segment is 1/2. Yes, that's 1/2. And I take 4 segments of this. Okay, these are 4 segments. So n in this notation, n equals 4, and h equals 1/4. So the error of h of the integral calculated with h being 1 is this, and the error with h equals 1/4 is this, and it really goes like 1/4 to the 4. Okay. Questions? Oh, so that was the Simpson method, and now I will talk a little bit about errors, just for you to see that we do the errors correctly, but we will not succeed. And I will tell you how to make this, but we will not do it. But at least you have to see in the course a rigorous way of finding the error. Okay, so now we will talk about this minus h to the 5th over 90. Again, we will not find it, but at least we will talk about it in some rigorous way. Okay. Okay, so let's again suppose that we would, yes.
Here, how did we, I know you chose to separate it for segments. How do you know How many segments do you need?
I only try. If I don't know the answer of the integral, so I try an h, and then another h, and then another h, and I see what's the difference between the answers that I get. And I see that this difference decreases and decreases. So I will know that my answer will be precise up to the second digit or third or fourth, depends on these differences.
In these examples, we're talking about cases where we have a function and we know the function, but we want to find its integral.
Yeah.
It's interesting because we use the same method to choose the best sample rate in an experiment. Well,
Of course, right.
like it's the same thing.
Yes. Again, when you do an experiment, you also have an error of measurement. So you can call it somehow like the round of errors. So there is also an optimal H there.
Yeah, that's what I'm thinking. So.
Yeah. So and this error, if it's a round of error, which is only by one digit, so the same way of our calculation is correct, or previous calculation, but maybe this error of measurement is somehow statistical, and then there is H optimal in a statistical meaning.
Yeah.
You have to make expectations and variance and optimize. Yeah.
How we go back? How when we calculate the error, how does we know that it depends on h in power of 5? Like it's the fourth derivative, and
How did we know this? You asked.
yes, I understand why it's the fourth derivative because it's a third degree polynomial, but why it's h?
So it's a quadratic polynomial. So your question is a good question. We'll talk about it. Okay. So it's a good question that you had somehow to ask before, and we'll talk about it now. So let's go back to the general M. Again, when M equals 0, this is the Riemannian approximation. When M equals 1, this is the trapezoidal. When M equals 2, this is the Simpson third rule. And when M equals 3, it is the Simpson 3/8 rule. And with a general M, what's our method? So this to interpolate the function here with these M plus 1 points. It will be a polynomial of order what? Order M. And that's how we build it. Yes, we build these LJs of X, where each LJ of X is a polynomial of order M that equals 1 at Xj and equals 0 at every Xi, which is not the Xj. And our interpolation is the sum of these polynomials multiplied by the values of the function at the x's respectively. Okay. So this is a polynomial of order n that equals yj at each xj. And again, in interpolation, we assume that the yj are the evaluations of the function at xj, exactly on the side. And how do we approximate the integral? We say that our approximation of the integral is the integration over this function, this interpolated function. Okay, so when we do the integration, we have these yj, and the integration over lj is some weight for this yj. So that's our method for the integral, for approximating the integral. And again, these wj's are the integrals over the polynomials lj's. And now we're asking about the error. Okay, so the error of the integral will be the integral over the error of the function. Okay? So let's talk about the error of the function. If I have a function and I interpolate it in n plus with n plus 1 polynomials, what is the error of this interpolation? So that's the first time that we will talk about this error, and here is a way that you find that error. Suppose, okay, so here I have my function x0, x1, x2, xm, and I have the interpolation. The interpolation says that f of x is something. I know what it is. Okay. Let's see. Start up yj, aj of x, j, 0 at okay. And I'm asking about some point, for example, here, called xp, and I want to know what is the error of my evaluation at xp. And again, xp is not one of these x's because the error at these x's is what?
0.
0. Okay. So how do I do this? I define a function f of x, f which depends on xp, f of x, which has m plus 2 zeros here. This is significant. Why do I do this? Because I want to use Rolle's theorem many times. So let's do it. So f of x minus f of x has m plus 1 zeros here. What are these zeros? It has m plus 1 zeros in this segment. What are these? Yes, the x0, the x1, the x2, because f of x equals f hat of x. I know that. Okay? So up to now, this function equals 0 at each point of the x. I add another function that also is 0 at each point of the x. It's a polynomial of order what? n plus 1. So this is also 0. And I want this function to be 0 at xp also. How can I do this? I multiply by some number. Okay, I call it cxt, which is constructed so that it will be 0. Yes, that's the c. Okay, so I want this at xp to be 0. So choose c to be that. And now, yes. And now this function equals 0 at x0, x1, until xm, and at xp. Okay. Now, because that function. Now, also we assume that f is differentiable k plus 2 times continuously. Maybe you can assume it's smooth also, infinitely. And using Rolle's theorem, we know that because this has k plus 2 zeros in this range, its derivative has what? K plus 1 zeros in the range x0 to xm. And the second derivative has k or m, I say k, m zeros. And you do it more and more until you get that the m plus 1 derivative of x has 1 0 at this segment. I don't know what it is. Call it psi. This psi will, of course, depend on xp. Okay, but call it psi. And I know that the m plus 1 derivative at psi equals 0. What is the derivative, the m plus 1 derivative of this? M plus 1 derivative of this. 0. This is a polynomial of order m. This is 0. And what is the m plus 1 derivative of this? This is a polynomial of order m plus 1. And this is this multiplied by what? I'm asking about this. What's
M plus 1
n plus 1 factorial? Okay. So I know that at the point psi, there exists a point psi that at it, I have that the n plus 1 derivative of this minus 0 plus this equals 0. Okay. Therefore, this C, which is this, also equals this divided by n plus 1. And therefore, f of xp minus f hat of xp equals this. So here is a formula for the error at xp. So if you want the error of our evaluation at some x, it is the multiplication of that x minus xi for every I divided by n plus 1 factorial multiplied by the evaluation of the n plus 1 derivative of the function at some sum, which depends on that x.
That's only function.
So
How do you find this value?
it depends on the function, but it is as a function depends on on x. Okay, it is the derivative of the function depends on.
No, I'm just saying, like, how is this useful? How do we use this? We do not know this value.
How do I use this? What's the meaning of this? I know that my error is this, and if I know what's A and B, I can, for example, find the maximal value of this. Okay, so that if I know what's this derivative, okay. But what's good for me when we use it with h, you will see we have this multiplied by h to the power of something, and that power is what is good for me because this is a constant. This is bounded by a constant, and I control h. And so when I don't know the function, again I make the steps and I compare each step with the previous one.
Let me explain what the meaning of that fx has at least m plus 2 zeros in it. What the meaning of fx has at least m plus 2 zeros in it.
It has 2 zeros. It has. I don't know if it has more zeros. Okay, I don't know, but it has at least n plus 2 zeros. Here are they. By construction, zeros means that it equals to 0 at n plus 2 points. Roots. Zeros mean roots.
Why is it 0 again?
because this CP is the- I only ask for this to be 0. Make it 0. So CP is f hat of x minus f of x p x p minus xi. So when you c of xp, so only plug in xp here, and this would be this minus itself. So it's 0. I build it like this. Okay. It's clear? Any questions? So now for the first time, we talked about Lagrange interpolation, but for the first time you get the error of that interpolation. Okay. And now I will try to find the error of the integral. So the error of the integral is this. Okay. So the error of the integral is the real integral minus the integral of the interpolated function, which is the integral over this, and we don't forget that this psi depends on it. That's very important. And now I will try to use the mean value theorem for integrals, which states the following. So if f is continuous and g is Riemann integrable in AB, then there exists psi at AB or in AB such that the integral of f of x multiplied by g of x from A to B equals f of psi integral g of x dx. And there's something that I have to add. But this is true when G also it is Riemann integrable and does not change sign. Okay. So I want to use this. But this function here, what is the G, changes. Okay. So there's a problem with this integral. Not a real problem, but what I have to do something. This thing here is only change of variable. It's not important. So this function here changes something. For n equals 1, there's no problem. For n equals 1. Why? Because it doesn't change sign. Okay. For m equals 1, there is no problem. So for n equals 1, what do? This is the multiplication of x minus x0 and x minus x1, and the integral is from x0 to x1. So this does not change sign. Therefore, I can take this out and say there is some psi and multiply it by the integral, and I can calculate this integral. It is minus h cubed over 6. And this is the minus h cubed over 12 multiplied by the second derivative for the trapezoidal rule. Okay. So that's a rigorous way of proving the error for the trapezoidal rule. Okay. This is the first time you see this, I think. Okay. Because again, I have to use this theorem, and when you saw in previous recitation, you will see that there is an expansion, and we take this h cubed, the term of it, which with the term of h cubed in the interpolated function, and somehow sum them or subtract them, but they are not in the same point, not in the same side. So you have to do this. But again, if I want to use this rule for m equals 2, for example, then for m equals 2, yes, I have a problem. M equals 2 means I use 3 points. Okay, so this is m equals 2, not 1. Yes.
Did you explain again what Riemann integrable is?
Riemann integral.
I know it's integrable. What is Riemann?
For example, if it's continuous up to some point or 2 points or 3 points,
Oh,
it's
intermittent.
Riemann integral. Yeah.
I don't know that.
Riemann integral, that means that the Riemann integral converts. That's Riemann integral. This sum converts. Okay, that's Riemann integral. There is another integrability. Okay, not so only Riemann. There are functions that are not Riemann integral. Yeah? But
I don't think we encountered this definition in our courses so far, but maybe I'm wrong.
what's the meaning of integral?
You created.
Riemann in a Riemannian way. You
I don't know whether
you
you-
learned only the Riemannian integral.
Okay.
There are another integration.
Oh, yeah, I think.
Why G can't change sign?
Mhm.
You write that G does not change the sign. Why?
Why?
Yeah, why it's a mass?
You can think about it graphically, okay? About this theorem graphically, and I can tell you all this. Think about it graphically, and you see
You have made
that if you average over also, this is some averaging. Yes, you can divide by b minus a. This is some average. Okay. So you can think that if you can see or check that if G changes sign, it's not definitely true. Okay, I think you know the simple version of it when f equals 1. Okay, you know that when G equals 1, so you know that f of x integral from a to b divided by b minus a equals to what? If f is continuous, f of some. Okay, when c is between a and b. So this is when G equals 1. Take G, what? Take G equals 1 and minus 1, and we can make the integral be 0. Okay, so
Okay.
you can take examples for it. Okay. So with m equals 2, I have a problem, but I can solve it. I can say that this integral from x0 to xm is the integral from x0 to x1 plus the integral from x1 to x2. Okay, and that these segments, this g is constant. It doesn't change sign. Okay, and then I have this at some point psi1 multiplied by the integral plus the same thing at some psi2 multiplied by the integral from x1 to x2, etc. And these integrals will change sign. You will see that these integrals will change sign. So you will have the answer of multiplied by the integral of this plus something multiplied by the integral of this from x0 to x1, from x1 to x0. And that's the error, that this will be m plus 1 at psi1. This will be f m plus 1 at psi2. And when I write this like this, I can only bound this error. For example, I say that this error is bounded in its absolute value is bounded by the absolute value of this plus the absolute value of this plus the absolute value of this, and then make somehow find the maximum of this at A from A to B, and give a bound. But this bound will not be h to the 5th divided by 9. This will be another bound. Okay, and it will be, for example, h to the 5th divided by 6 or 12. I don't remember. But we can find that h to the 5th divided by 90 with the minus sign also. I will not do it, but at least you've seen how we can find the error in a rigorous way. How can we do that? The answer is for this, for m equals 2. The answer is it goes like this. We will try to interpolate the function between x0 and x1, x2, sorry. We have x1 here, not by a quadratic polynomial, f2. We will make an interpolation using cubic polynomial. We will not do it, okay? But I'm telling you how you can find that L, h to the 5th divided by 9. This polynomial, I will ask it to be equal to the function here, and the fourth condition. This fourth condition will talk about the derivative here at this point. When I do this, I will get a polynomial. And when I calculate the integral over it, magic, it equals to the integral over it. Okay? So this Simpson way is also this way, but I choose the condition here such that my error will not change sign and from x0 to x2.
Make sure what you're saying, increasing the polynomial line from second order to third order does not reduce the error. Is that what you're saying? Or it doesn't change the error?
It does change the error in the interpolation, but when you make the integral, it doesn't. Yeah. So when you make but you choose your condition in a very clever way. So your condition will talk about the first derivative here, and then the error that you will get will not change sign from x0 to x2 because it will have not x minus x1, it will have x minus x1 squared. So it will not change sign in the range.
So the arrow will not change, but will the value of the integral will change?
It's the same error, okay? But the question is, how can I find a closed form for it? Closed formula, okay? So I'm telling you that if I choose a good polynomial here, that its error goes like not x minus x1, but it goes like x minus x1 squared, the integral over it will equal the integral over this. Will be equal. Which is what? Which is this. You will find that the answer is this.
I'm confused as to, like, are we saying we can make the cubic spline interpolation as bad as the quadratic spline, or can we make the quadratic spline as good as the cubic spline on the integral? Like after we make it.
After making the integral, they're the same.
No, but you're saying only if we take the right condition on it, right?
The right condition for me in order to get a good formula for the error. Any interpolation that I take here will get me an answer with an error. The question is, how can I write down this error?
So the only way to get an error evaluation, like a good error evaluation for the cubic spline, give us the same error as for the quadratic spline.
Yes, but the cubic spline here will not use, at the end, will not use another point. It uses only these 3 points.
This is very weird because the cubic spline follows the function more accurately.
But it's not a cubic spline using 4 points. After we finish that, it's only the 3 points. So you will find somehow in many places that they prove the h to the 5th divided by 90, not like this. They prove it like what I said before. They expand something and expand something and take this minus this or plus. It's not correct proof. Okay. So at least now you know how to prove it, or you have some notions, ideas to prove it. And the main idea is that I have to use at the end the mean value theorem for integrals and evaluate the integral, this integral, and then take this out and then calculate this integral. Not exactly this, maybe, but calculate the integral over some polynomial. Questions? Okay. So let's talk about the trapezoidal rule when we talk about all this. So now go back with m equals 1. M equals 1 means that at each segment we have 2 points, which are these points. We know, for example, if the function is this, so we take this, this, this area, this area. That's my trapezoidal method. So my evaluation is we have of f of xi plus f of xi plus 1, sum of it, h, and I goes from 0 to n minus 1. Okay. And at each segment, we have proved, right? Right now, we proved this. At each segment, my error will be minus h cubed over 12 multiplied by f double prime at some psi I in that segment. I have psi 0 here, I have psi 1 here, I have psi 2 here. So I will have this error. Okay, and again, this is a sum of n. Why? What?
Why would you have that error?
Because my integral is the sum of integrals, which are xi to xi plus 1 dx. This is my integral, okay? 0 to n minus 1, 0 to n minus 1. That's the exact one. And the approximated one is same with these. Okay? It's the same, but only put hats. Okay? So now, what is I minus I hat? It is the sum of I minus I hat. That's my error. You agree? Yes? Now, the error, this is the error of my trapezoidal rule when I use it here. Okay? So what's my error? I have proved that my error is minus h cubed over 12 multiplied by some by the evaluation of the second derivative of f at some psi I, where psi I is between xi and xi plus 1. Okay? And now I have minus h squared over 12 multiplied by h because it's h cubed. So what b minus a over n, that's h. The sum of f double prime at psi I. And this is f double prime at some psi in the range between A and B. So my error goes, that's what you know before, that my error goes like h squared or 1 over n squared, where n is the number of the segments. So now we have proved this well. And I want you to notice something before we go to the break. What is this? If n is very, forget this. What is this? If n is very, very large. Approximately what's it?
Small. Small.
No, not the n. All this. All this.
No, but when n is very large, then the derivative is very close. The function is closer to linear, so
No, this is the real function. F,
Goes to 0.
the original function. What?
Like that fraction just goes to 0.
No, I'm sure. What is this? If you have a continuous function, g of xi,
The third derivative?
okay, I will draw it. If this is g and n is very large, so I take many points here, many points,
Yeah.
The third derivative.
and yes, what?
The third derivative.
Yes, it's the integral what over b minus a. It is the average of the function. It is the average of the function.
Oh,
And again, approximately. Okay. So if n is very, very large, this is the average of the function plus a correction, a small correction. Okay. You agree with me? All of you? Oh. So we recall the recursive way. Okay, you recall the recursive way of the composite trapezoidal integration. We take Hn and calculate the integral, and then we take Hn plus 1. Hn will be 1 over 2 to the n. Okay, and then divide more, multiplied by 2, the number of the segments. So we know that if we calculate the integral recursively with 2 to the n points, or 2 to the n segments, that's my error. And if we calculate with 2 to the n plus 1, that's my error. Okay? But this is the average of the function using 2 to the n points. This is the average of the function using 2 to the n plus 1 point. But it's also the average of the function. If n is very large, this is the average of the function plus a small correction. And also this is the average of the function plus a small correction, not the same correction. Okay?
The smaller one.
Yes. We think. Okay? So if I call, and don't forget that Hn plus 1 is Hn over 2. So this will be Hn squared over 4. And if I call this C plus a small correction to it, this is also C plus a small correction to it. So I have two ways now of calculating the integral, this and this. Each one of them is approximately this. This is C plus epsilon 1. This is C plus epsilon 2. Okay? Okay? But multiplied by Hn squared. So I have an evaluation for the integral. Which has an error of C plus epsilon 1 Hn squared. And E, another way, which is C plus epsilon 2 Hn squared over 4. Therefore, I can cancel somehow this Hn squared. How? If I take 4 of this minus 1 of this divided by 3, I will get the integral with an error. What's the error now? So if I take 4 of this is the integral, In plus 1. This is the integral with an error. Okay? And this is the integral with another error. If I take 4 of this minus this divided by 3, this is the integral plus an error. What's this error? This error will be C Hn squared plus epsilon 2 Hn squared minus C Hn squared minus epsilon 1 Hn squared. So it will be epsilon 2 minus epsilon 1 for epsilon 2 minus. I'm sorry, epsilon 2 minus epsilon 1 Hn squared, which is much less than Hn squared itself, because the epsilon goes like at least H of Hn squared. This epsilon depends on H. Yes? This epsilon depends on H, because this epsilon is my error of this approximation. So if h is smaller and smaller, the epsilon is smaller and smaller. So now when we found before in a recursive way, if you remember, R0 and R1 and R2 and R3, here we used hn 1 over 2 to the n. When we found this, we said that with this recursive way of trapezoidal error, what was our error? It was O of h squared. Okay. Now I can use this and this to get something else. I call it R tilde, which will be only 4R3 minus R2 divided by 3. This I found before. Only I do this, and this will have an error of h to the 4, not h to the 4.
I'm not playing the, can you explain it again?
No. Now take a break, and after the break, I will. Okay. So again, what we are doing now, and I'm repeating what I said before, but this is a motivation for the next step, which is the Romberg integration. So we get the motivation from here and then continue. So what's the motivation? What does the motivation say? Says that we know how to calculate using the recursive composite trapezoidal way. We divide this, the range of integration to 2 to the n segments, where n is the step that I take, the number of the step, and find the trapezoidal integration using these segments. Okay? At each step, the h is less than the previous one by a factor of 2. Oh. And I have an equation of the error. Okay, I have a formula. That's the formula of the error using any hn I want, any h I want, including the hns here. Okay. So the formula says that if you find the integral at this step using, so what's this integral, for example? For example, if I use 4 segments, what's the meaning? What do I calculate? What's I4? What's I4? What's I4? It is
Using the
the integral from a to a plus b minus a over 4. Okay, that's h. Okay, plus the integral of a plus a plus 2h plus the integral a plus 2h to a plus 3h plus the integral from a to 3h to b, which is a plus 4 plus 4h. And this integral I calculated using the trapezoidal method. Okay, what is this? This is the half of f of a plus f of a plus h plus this and this and this. At the end, what do I get? I get h. I get h. What's the h? It is h2, which is h. It's not 1 over. It is b minus a. So the answer is h over 2, f of a plus f of b. So it's h plus the sum at the points 2 and 3. Okay. So that's our formula. And we know that the recursive formula is, if I know what is the I before, I know that the recursive formula is in equals the half of in minus 1 plus hn multiplied by the sum of f evaluated at a plus 2i minus 1 hn, where I goes from 0 to the n minus 1. Okay. So that's
I
the
think the -1 is not, low, the -1.
maybe you can check it. And I think it's the okay. So I know that if I calculate this I1 and I2 and I0, I1, I2, I3, I4, I will get an approximation of the integral up to an error. This error is the average of the function plus an error. Okay. So if n is small, this error will be big. But if we are at large n's, this will be approximately the average of the function. So it's the average of the function multiplied by a constant multiplied by hn squared. So the error, if we compare two steps to a different step, the error of them will be 1 c plus epsilon 1 hn squared, and the another c over 4 c plus epsilon 2 over 4 hn squared, because the hn plus 1 squared is hn squared over 4. Okay? If n is very, very, very big, you will see that it doesn't have to be very, very big, because if n equals 5, that means that we use 32 points. Okay? 32 segments. But if n is very, very large, this is somehow the integral itself, the average. So we can, if you assume that this equals c and this equals c, I can find an approximation of the integral which doesn't have any error. Why? Because take 4 of this minus 1 of this divided by 3, there's no error. If this equals c, okay? But it doesn't equal c exactly or precisely. It equals c plus epsilon 1 and c plus epsilon 2, where epsilon 1 is something that is very small because h is, and epsilon 2 is small because h is small. So we hope that, not only hope, we know that this will have an error not of order h squared, because we made the error of order h squared cancel out. Okay, so this will be of order of h to the 4th. That's what we expect. Is that clear?
What?
At least h to the 3rd. At least. because this is the average of the function plus a correction. This correction goes like h at least. You know that it goes like h squared. Okay. So again, we now can calculate from the list that we calculated before. We can calculate updated values, which are I1 minus I0 divided by 3. And here I can calculate I2 tilde, I3 tilde, I4 tilde. Okay. I2 tilde is 4 I2 minus I1 over 2, etc. And this will be O of h squared, hn squared, and this will be O of hn to the 4th. That's our hope. We know that they are better than hn to the square, hn squared. I tell you that it's h to the 4th. Okay. So now we know that there is another formula that it's better than this. If we have this, if we already have this. Okay. This is the motivation, and now we will see how we can prove it in a more better way. But we will prove it using some formula that we didn't prove. Yeah, we want to. This formula is the Euler-Maclaurin summation formula, and it will take us to the Romberg method. I have to tell you that this thing that we did, it's called Richardson extrapolation, and we will use it now, but we'll see the proof of it. So this summation formula, you can find it in Wikipedia with f of x integrated from an integer to an integer. Anyway, you can write it like this, and it says that the integral of f between x0 and xn is the trapezoidal integral. It is the trapezoidal integral plus a correction. Now, this correction, I can write it up to an order p, and add another correction, which is the integral which is an integral using Bernoulli polynomials. But these are Bernoulli constants, and I know that this is true. So I know that the trapezoidal rating is the function plus a correction, which is constant multiplied by h squared plus a constant multiplied by h to the 4th plus up to some order plus a correction integral. Okay, but what is important for me that it's h squared and h to the 4th and h to the 6th. It is important for me for you to know that this expansion is an asymptotic expansion. Okay, so if you don't know what's an asymptotic expansion, you will know in methods 2. I will be also there. But I can say that at a given age, there is some point in this sum that it's better for me to cut the sum there and calculate the correction. The correction doesn't go to 0. Okay, if you take more orders and orders, the correction will be larger. So there is some order where the correction is minimal and for every age, for every given age. Okay. This doesn't matter for us here. What we can see from this that the integral equals in, for example, take n to be 2 to the n. So the integral equals this. And take n to be 2 to the n plus 1, the integral will be this. What is important here is that this and this doesn't depend on h. Okay, they don't depend on h. So we see here, and we have here to put hn to the power of hn plus 1 to the power of 2k, but hn plus 1 is hn over 2, therefore this is hn to the 2k over 4 to the k. Okay. So now let's look at the first term here. The first term here is this multiplied by b2 over 2 multiplied by hn squared. And this is the same thing multiplied by hn squared over 4. So if we take 4 of this minus 1 of this divided by 3, we will get this integral plus a correction. What's the correction? It's only take 4 of this minus 3 of minus 1 of this divided by 3. That's the correction. But now this correction, the first term of it is 0 because I canceled it. I took 4 multiplied by this minus this in order for h squared to be cancelled out. Okay, so for k equals 1, this is 0, and my error starts with k equals 2, which is h to the 4th. Okay, so my error now is h to the 4th. I proved this for you. But now you can see that my error, here it is. Okay, let's go down. I made change of variables, so it has to be here plus 1. Okay, there's an error here. It has to be plus 1.
You fix it before you upload the like will you fix it before you upload it to the Moodle? You know,
It's not fixed.
what?
Hmm?
Is it validated? Can you upload a correction to it?
Ah, okay.
That's what I mean. So we have like the right stuff.
Okay. So now I have better evaluation. Okay, using the previous ones, and they are of order. Their error is of order h to the 4. Now let's look at I tilde n plus 1 and I tilde n. The tildes. Also, this error doesn't depend on h except here. Okay, so here and here. Okay? So you have this constant. This depends on the function at the endpoints. So I tilde n has an error of h to the 4th and etc. And I tilde n plus 1 has an error of h to the 4th and etc. So I can use them and make this h to the 4th cancel out. Okay, so how can I do this? Look at the first term here. What's the first term? The first term is hn to the 4th. Okay, It's hn to the fourth. Multiplied by something. And if we look at I tilde in the previous n or in the n plus 2, for example, it will be the same but multiplied by what? Or divided by what? Or squared, which is 16, because it's hn to the fourth. And hn plus 1 is hn over 2. So take this to the fourth. It is hn to the fourth divided by 16. So if we take 16 of this minus that divided by 15, we will get a better approximation. So here, huh?
It's a lot more computational work.
Let's see. It is only so it will be n squared. If I calculated this, so it is of order n squared. This is n. So I have n of order n squared calculations. So I2 tilde will be 15 of I2 tilde minus C minus I1 tilde over 15. And I can find another column which has an error of hn to the sixth. So again, at first we calculate this, which is only what? Yes, it is only b minus a over 2 multiplied by f of a plus f of b. That's this. And then we calculate this recursively using this. And then we calculate this column using this, for I minus I. Always I use these two. And then I use these two. Therefore, let's build the triangle. Okay. So that's our triangle. Okay. So we have here 4 to the I. Okay. That's our way. So again, we calculate this at first, and we calculate this recursively, and after that, we calculate each column from the previous column. And we know that this is better than this, 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 this is this, and this is the best.
We don't need to go all the way down the triangle, right? Like we can stop whenever the error becomes smaller than our Mentissa error. Right?
That of course, yes. But I thought you would say our error will be less than some criteria that we fixed before.
Yeah, but like we can literally get to like this will stop changing at some point if like under the right conditions.
Of course.
Like under the right conditions, like half the triangle will be the same.
Yeah.
It's just evaluating the same thing.
Yeah. So generally you have this infinitely, and you have an infinite triangle, and you can stop wherever you want. And if you stop here, I can say that you looked at this triangle. Okay.
So like the most efficient way to do it is to not go down one column, but like go down by rows, and that way like, you find the
Before all,
best
I
areas.
know this order. I can make a conjecture for the order that I want. But I know this.
Oh, so you just know what column you're trying to.
Yes.
Okay.
So I can take an approximation of, because of knowing this, I can take an approximation of the order that I have to take or the number of the steps. I'll try and check what.
And if it doesn't work, I just take one more.
Yeah.
going,
You have to take more in order to see the difference, because you don't know the real answer.
Yeah.
Always you have to take one more or two more to see the differences.
what will converge fast? Going this way or going this,
Go this way. or-
like doing this method or just like we did in the exercise, that we just took more n.
I think we just answered that, like, you wanna go to the right, not down.
Yes, but she asked, what is faster?
What will converge faster?
Faster. Here, if I want, of course this, because this is of age. I thought about another question that I don't know the answer.
It might be computation even faster to just go down the column.
You always
Yeah.
want to go to the right.
No, like you might be able to like optimize the calculation going to down one column.
Yes, but it's h to the h squared, and this is h to the 10.
Oh, yeah.
So let's take an example. The natural logarithm of 2, you know that you can find the natural logarithm of 1.1, for example, using the Taylor series, ln of 1 plus x. But for example, here you cannot use the Taylor series, or if you want ln of 3. And what is ln of 2? It is the integral of 1 of x from 1 to 2. So we use a numerical integration in order to evaluate or approximate this number. And that's how we do it. So I built here the trapezoidal way, not recursively, okay? I only solved that it's h of the 2, f of a and f of b, and the 2 of the sum, 2 multiplied by that. So I made it not recursively. And then I defined Richardson extrapolation using k times. So it's the first extrapolation, the second extrapolation. And as you saw, I changed my my notation. This will be R00. This will be the number of steps of extrapolation, of Richardson extrapolation. So here at this column, I didn't do this at all. So R1, 0. This is R2, 0, R3, 0. And 1 tilde is one step of extrapolation. So it is R1, 1. This is R2, 1. This is R3, 1. Okay, so that's the notation now. You can see it also here. That's the notation.
Thank you.
And of course, I defined the first column to be the trapezoidal integration defined before. And after that, recursively, I find each column from the one before. And I can write this 16i n plus 1 minus in over 15. I can write it as in plus 1 plus in plus 1 minus in over 15. So that's the way I wrote it here. Okay. Yeah.
Why you call this extrapolation? Why extrapolation?
Because you take from here to here. So you because it's not the same.
It's not the same range of.
Yeah. Because the error here will be at psi i's and the error here at another psi. Okay, And also I built the triangle, so I printed it as a triangle, so that's it. Okay. So I built this triangle and return R, return a matrix of a two-dimensional. This R is a two-dimensional list, so it's a matrix, and it will be zeros here, and the values will be at the right places. So I print only that these values, and this result I write it here, and compare with the original result. So the exact value of line 2 up to the 15 digit is this, and you can see in bold the digits that are true. Okay. So so you can see that we are 2, 4, 3. So we are good up to 10 to the minus 9.
That's incorrect.
What?
Like the last digit should be, I guess, oh, if you approximate that digit, it's one.
Yeah. Okay, and that's our way. So you can see that this goes like this, and you can see how we improve, and we improve from here to here, and from here to here, and from here to here by what? By h squared. What is h? What is h here? 1/16. So we improve the error 16 times. We expect that. Okay. Maybe it will be true, maybe it will be not true, but we expect this convergence with large n's. And that's our way of approximating line 2. And you can check for yourself what's going on with pi. You know, pi, you can approximate it using many formulas. And here we can use this formula of approximating one. The integral of 4/2 of a polynomial divided by a polynomial. So this is something that I can calculate, and we use this Romberg integration in order to evaluate that pi, and you can check for yourself how many steps you have to do to get to that. Any questions? Okay, so your homework will be uploaded tomorrow, not today. And see you next week.